When we first start to learn about mathematics in school, we might learn to read functions such as this function here, this polynomial function, which takes some variable x and then squares it, multiplies that result by 3, and adds 4. Right? We all learn to read these kinds of formulas. What you might not have learned, perhaps, is that we can make this order of operations very explicit. And we might write this like this. So the dot here is function composition, and we read this from right to left. So we first apply this function, which squares its argument, then multiply the result by 3, and finally add 4. Right? So these two things are equivalent. The bottom one is just much more explicit about what happens when. So function composition is a very simple concept. Right? It just means apply one function, then the next, then the next. Monads take this idea and generalize it to programs. First apply one program, and then the next. That's all monads are. And we'll make that connection very precise in today's episode of the Haskell Unfolder.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and to discuss them.
Right, so before we look at more code, I want to think a little bit more about this dot thing here, this function composition. And so we write it like f.g, meaning first apply g, then apply f. And the definition is very simple, right? It just means take g, apply it to x, and then apply f to the result. Okay, so let's think a little bit about the properties of this function composition. And in particular, what happens if we have 3 functions here? Okay, well, we can apply the definition, right? So we have f on the left, and then instead of g on the right, we have g.h on the right, okay? We just apply the definition, f on the outside, g.h on the inside, and then we apply the definition once more on the inner thing here. So instead of f, we have g, instead of g, we have h here, and we just apply it again. Right, and then this is the result that you might probably expect. Take x, apply h, then apply g, then apply f. And if we stick the brackets on the other side, right, so the brackets on the left, then when we apply the definition again at the top level, then we have f.g instead of f and h instead of g here. So we apply that, and now we have f.g, but the argument is no longer x, the argument is h of x. So we apply the definition where h of x for x here, and we get the same result again, right? So we just take x, apply h, apply g, apply f. So the conclusion from this is it doesn't matter where we put the brackets. So we can leave the brackets out completely, and f.g.h simply means first apply h, then apply g to the result of that, and then apply f to the final result.
Mm-hmm.
Okay, simple enough.
Associativity.
Associativity, yeah, that's the mathematical property here. Yeah, exactly. Mm-hmm. Now, the other property that we want to think about is what happens when we compose, like this function composition, with the identity function, the function that does nothing, right? That just returns its argument unchanged. So we might ask, okay, what is f.id? Well, we can just apply the rule for composition again. It's f applied to, id applied to x. id applied to x is just x, so this is just f of x. Mm-hmm. Right? And similarly, if we have id on the left, applied to x, I beg your pardon, there's a typo here, then we apply id applied to the result of f applied to x, and so now we have id applied to f of x, right? And we just that's why the definition of id is just f of x, right? Again, this is just equal to f of x, meaning if we stick id on the left or on the right of f, then the result is just f, right? So I want you to remember these two properties, right, of function composition. One is that it doesn't matter where we insert the brackets. f.g.h just means apply h, then g, then f. And if we stick in id on the left or on the right, it just does nothing, right? It just leaves the function alone. Okay. Hopefully that made sense. So now let's think a little bit about code. But before we look at Haskell, I want to look at C first.
Ooh.
Yeah, very controversial. So let's suppose that we have this function fun_a in C, which takes an argument x, and what it's going to do is it's going to print the string hello, and then return x plus 1. And maybe we have a similar function b here, which also takes an argument x, and it's going to print world, and then return x plus 2. And maybe we have some main program here, which is going to call both of these functions. then maybe print the final result, and then return. Right, and so what we expect to happen is that we see hello world printed, we pass 1 to the first one, so that would be 1 plus 1 is 2, we pass 2 to the second one, 2 plus 2 is 4, so we expect to see 6, I guess. So let's try. We run this program, and that's exactly what we see. Okay, that all seems very straightforward. But mathematically speaking, if we think a little bit about this expression here, then mathematically, if we have two values, x and y, then surely x plus y must be the same thing as x plus y plus x, right? Surely these two things are the same, mathematically speaking. But I guess everybody knows that if I flip these two things around, I don't get the same program, right? Because if I now run it again, like my output is messed up, right? I see world before hello. So what went wrong? Now, plus is adding numbers, but we're passing arguments which are programs which return numbers, right? And C's type system does not make that distinction. And that's why we cannot really do mathematical reasoning in C, because we don't have this distinction between programs and values returned by those programs. So in Haskell, we do make that distinction, and that's where monads come in. So let's think about the same two programs, right? Fun A took an argument, right, and returned also an argument. And it printed this hello string, and then returned x plus 1. And we did the same thing for function B, right? It just printed world, and then returned x plus 2. And then in the example that we had, we were trying to do something with, I'm using undefined here to say like we're doing something with this result. The important part is that we were trying to add fun A1 and fun B2. This is what we tried to do in C. And in C that just worked, except that it had weird mathematical properties, or rather it lacked mathematical properties. In Haskell, we get a type error here. And saying the type of this guy here, the left argument, is not int, it's not a number, right? It tells you here at the bottom, it's IO of int, it's this guy. What is IO of int? It's a program that when you run it, returns a number, but it's not itself a number. And so it's complaining here that I'm trying to add I'm trying to add programs, things of type IO int, but IO int is not a number, so I can't add them. And so in Haskell, we make this distinction between values and programs that return values very explicit.
And that's a good thing, right? I mean, you're going to say that anyway, I know, but just because you already said, like, because for numbers we would expect that we are able to flip them around and get the same result, whereas here we have to make an explicit decision in which order we want to run these programs, right?
That's right, yeah. If I see something x plus y somewhere in my Haskell program, I know I can always replace this by this, and it will be the same program. Right? This mathematical law does hold in Haskell. And indeed, if I have programs here, then I need to make a call. I need to make a decision, like Anders said. Do I call A first or B first? And I need to be explicit about this. All right. So we started the episode by looking at function composition. So let's briefly go back to that again. And we had this example, right, where we had 3x squared plus 4. Now we could write this in Haskell in the exact same way, or nearly the exact same way that I wrote it in the mathematical equation. Right? And what did we do there? We said, well, we first take our argument and square it. Then we compose it, right, with the function that multiplies its argument by 3. And then finally, what we do is we add 4. And this is a perfectly valid definition in Haskell. And this is direct translation of what we had in mathematical notation earlier. So if we think about what the type of dot is, right, the type of function composition. So it's going to take two arguments, which must both be functions. Right? And it's going to return a new function. Now, if the first argument, so this is the first function we're going to apply. Remember, we're reading this backwards, right to left. So if this function takes an A and returns a B, we don't know what A and B are. We don't really care. And then the second function will be applied to the result of the first. So that must be a b. It's going to return some c. We don't know what c is. We don't mind. And then the final result is going to be a function which takes that a as argument, the first input, applies both functions, and then finally returns that final c. Right. So the type of function composition in Haskell is this. Okay. So why are we talking about function composition when we want to talk about monads? Well, if we have programs which might have this shape here, right? Some argument here, there's the arguments to the function, to the program rather, and then IO. Remember, this is a program which returns a result when you run it, and then some final result of this program. Right? Then we must be able to compose them in the same way, like first do this program, then the other program. So if I take this type of dot, I can now give you the type of program composition to compare against each other. And if I just line these up a little bit better, we can make this very, very explicit. As you can see, these look almost identical. The only difference here is that in function compositions, we're just composing functions. In program composition, sometimes called classically composition, we compose programs. And so you can see by comparing these two that they are identical, right? Or all nearly identical. The types look very, very similar. So let's see an example. Suppose I have this program called askName, which takes a prompt as argument. What it does is it outputs the prompt to the console and then just asks for some input. And I might have a program say hi that takes some name and then just outputs that name to the console with hi and then the name. Then I should be able to compose these two with our program composition operator to get a new program that outputs this prompt, asks for a name, and then prints the name. All right, so let's try that. We still have the input, right? That's the final result is the A, right? The prompt is still not defined. And we just compose these two things. So let's try this.
And it is part of the spec of this composition that the effects happen in order right to left, right?
Yeah, just like function composition says, first apply this function and then apply this function. Program composition, that's the exact same thing. First run this program, then run that program. Now you might prefer to flip this around. Maybe it's more readable if you flip it the other way around. That's convention. That's easy to define. Okay, so we could try this meeting. So we could ask, what is your name? That might be our prompt. And so we can see it asked me this. I type in my name and it says, hi, my name. Okay, good. All right, so we've seen that program composition or monadic composition, because that's what a monad is, and function composition look very similar. Now, in the introduction, we talked not only about what function composition looks like and how it's used, but also what laws it satisfies. Remember, we had this, like we said, that it doesn't matter where you put the brackets, and sticking an ID gives you the same thing, right? So we had these two laws. First one was associativity, like Andrew said. Brackets on the right or brackets on the left, doesn't matter. In both cases, it's just H, then G, then F. Now, we have an exactly analogous law for program composition, right? And it looks almost the same, right? If I have program composition with three programs, F, G, and H, then it doesn't matter where I insert the brackets. In either case, this simply means first run G, then run first run H, then run G with the result of program H, and then finally run program F with the result of program G. And we had the other law that we had, right, was this identity law that said if I stick an ID on both sides, then that doesn't change the function. And so what is the equivalent in term for programs? Well, we need for functions, this was a function that didn't do anything, that returned its argument unchanged. And we can have the same thing for programs, right? So we have a program called pure, which takes an argument A and just returns that argument unchanged. Right? It's just a program that when you run it, returns the value that you specified in the first place. And so once we have this program, then I can give you a similar rule that we have for functions, also for program composition, that just says if I insert pure on either side of a program, it doesn't change the program at all. And so what is a monad? A monad is any structure like I/O, and we've seen one example, we'll see more examples, that satisfies these two laws, where we have some way of composing, right? First run one thing, then run the other thing, in such a way that it doesn't matter where we stick in the brackets. And that has a way to stick it, okay, create a program that returns its argument unchanged, which satisfies this property that composing with that pure program doesn't change the program at all. And that's all. That is what a monad is. So we've seen one example, this I/O thing. It might be helpful to see a second example. Now, for a second example, I want to draw inspiration from a problem that's common in lots of languages, which is often called callback hell. Right? So in many languages, such as JavaScript, if you fetch a URL from somewhere, you want to have some contents from some location, then that's an asynchronous operation. And the way that it works is that you can't just call a function and get the result. Instead, you call a function and you pass it a callback, another function, which will be run once the result is ready. And so in Haskell, this might look something like this, where we have some URL to load and then a callback, which will be called once the result is available with the contents of that URL. Okay, so we might have this example here, where we get some initial URL, we fetch the information there, and perhaps what we get back is a redirect. Right, so maybe we get a new URL. Okay, fine. We fetch the contents of this new URL. Maybe we get another redirect, and then finally we get the contents of that final URL, and then we print the result. Right, and this is called callback hell because it gets very convenient. Right, like the more nesting you have, like the more steps you have, the deeper this nests. So can we do better? Yes, we can. So we could define something that looks like I/O, but that specifies background actions that run in the background. And as part of this repo, I have mocked up a very simple way that we might define such background actions. It's not really relevant how that's defined. If you're interested, there's a link to the repo in the video description. But for now, we can just assume that exists. And so we might have this function fetch URL background, which gets a URL, and that doesn't give you a program, an I/O. Instead, it gives you this background thing, which is another monad, meaning we can have composition, right? Composition, like we can do one thing and then the other, which returns the contents of this URL here. Does this help? Well, we can now define our example here, or almost our example, like this. We can just say we have the same function and we just compose one after the other, right? First do this guy, get some result out of it, apply that result, apply this next program to the result of the first, and then apply this third program to the result of the second. Right? And there's no infinite nesting. There's just everything just works. The one thing that's still missing is the print. Right? And if we tried to compose this with print, it would not work because print has type string to I/O of something, right? It's an I/O program. And this is a background program. So those two types don't line up. So we need a way to go from I/O to background, like saying, take this program and run it in the background. That's often called lifting. And so we can define print background to be something like this, where we take a string and then instead of I/O, we have this background thing here, and we just call the original print function and then apply lift to lift this I/O action into the background monad. And if this is confusing, by the way, the dot here, oops, like it's just the same thing as this, right? Function composition, program composition. Okay. Which means that I can now define my example here, but now using background. So I have some URL, the initial URL. And what I'm going to do, I call background, which takes a background action, something of type background, and actually runs it. What background action do I want? Well, print background composed with 3 redirects. And then I need to pass in some initial value here. And I can try this. So I'm going to call example background, and you'll see nothing happening. So I get my, so I do need to pass in the initial URL, beg your pardon. Right? Now nothing happens. I can just use my terminal here because the thing happens in the background. And at some point when it's ready, it's going to come back and it prints the result of URL 3 here.
Right. I mean, so normally it's not going to take that long. You put some arbitrarily large delay in there.
I mean, it might. Inside the world.
Haskell is not that slow.
Yeah, it's not the Haskell. It's a network. It's a network delay.
Yeah. Okay.
But yeah, this is completely arbitrary, of course.
Yeah.
This is completely mocked. Of course, this is not actual. It doesn't actually load anything. This is not a valid URL, obviously. But yeah, it just illustrates the point. Okay. So hopefully this all makes sense. What perhaps is somewhat confusing is that this might not look like monads as you might have seen it elsewhere. Like this operator often is not introduced when monads are first introduced, and it's maybe only often introduced much later.
But it exists.
It exists, yeah. I didn't make like it exists in the base libraries.
Just because we just mentioned that we've been like mocking things up. I mean, just wanted to highlight it. This one. Yeah, this is not in the libraries.
Yes, this is not mocked. This is the regular function. Yes. The function that we normally deal with in monads is called bind. So let's, if you haven't seen it, or if you have seen it and you're wondering how it relates, let's go back to bind now. Now this is the symbol for bind, and let's first look at its type. So it's going to take a program, like M could be IO or background or anything else, something that is at least a monad. And then this is the first program that we're going to run. And then a second program, which is going to take the output of the first program and produces a final result. And then we just need to compose them together to get a program that returns a B here. Now, there's two things to notice when we compare this to the type of what I've been calling program composition here. Let me just put it up here for comparison. Oh, sorry, that's the law. I beg your pardon. Where's the type? Here's the type. Like this. The first difference is that it's backwards, or maybe, depending on your perspective, forwards, right? It's first this, then this. Whereas for composition, it was first this, then this. So we take the arguments in opposite order.
Which, by the way, is like sort of the intended logic behind the symbols being used, right?
Right.
So the arrows going towards the right now, whereas before the arrows were going to the left. Yeah.
Right. Yes. Exactly.
And also, I guess, I mean, perhaps you were going to say this as well. Also, the composition operator, as you can see, is more symmetric because it takes two programs and composes them into a new program. And therefore, also the operator symbol is more symmetric.
Right.
Because actually highlights that sort of it's having equal things to the left and to the right, whereas this bind operator is a bit weird because it like turns a program, like a program which without a parameter and a program with a parameter into a new program. And so therefore the operator name is also slightly more asymmetric.
Okay, so let's think about how we might define bind if all we have is program composition. So we have F and G, and we want to do something with this. Now, if we just tried G after F, this, right, that doesn't work because G has the right shape, right? It has this shape, which matches this. But F does not, right? We want something like Anders said, with an argument, and we don't have something with an argument, right? We have something that doesn't take an argument. So we need to make a program that looks a bit like f, but does have an argument. So we can do that. So I can define f prime of type something to and a, so that I can apply it here. Now, what is the something? We're just going to pass in unit, right? Or like in C, it's sometimes called void. Right? And so it's just a dummy argument, which I'm going to ignore and then just call f. And now I can compose these two things together. But the result, oops, beg your pardon, if I stick in an underscore here to see what the type thing of this guy is, it tells me the result of this composition here is what is a new program that takes in unit as an argument and then gives me a b, right? Which makes sense. That's precisely what we had here, right? That a, we picked unit for a, so it makes sense that we now get a new program that still has an argument. We don't want that argument, so we need to provide that dummy argument, so we can just pass unit here. Now, normally in Haskell, bind is primitive, and this is derived, but they are equivalent, right? You can derive one from the other. And so I'm making the case here that thinking of this is perhaps more instructive to understand what monads are. In particular, if you have seen the monad laws in terms of bind, they look much more complicated than what we've seen here, right? I won't show them because we don't have time, but the important thing to realize is that those more complicated looking laws are the same laws, just in a different guise. But stated like this, they are much cleaner and much easier to understand, I think. Okay, so once we have this, now we could rewrite our 3 redirects guy here if we wanted to. We could write it like this, where we fetch the first URL, bind. So first do this, then do whatever, like the rest being this. Fetch the next one, get some URL, and then finally fetch the third one. And now, finally, like if you were wondering how does all this stuff relate to do notation, we can just write this program as this, where we use do, and then this almost looks like a C program. And do is just syntactic sugar, right? The compiler just takes this code and turns it into, into this code. These two programs are exactly identical. All right. The last thing I want to talk about is why we emphasize these laws. What goes wrong if we don't think about laws? And we have an episode, I think it's episode 8. I meant to look that up, I didn't. Where we talk about how to prove laws and things like this. And we'll put a link in the description. But I'm not going to do that today. What I want to do today is think about, like, very practically what goes wrong when those laws do not hold. So let's try and come up with a monad which looks reasonable, but actually fails to satisfy the laws, and see what goes wrong. Why do we care? Like, from a very practical, not mathematical, not proven properties, just programming perspective, why are those laws important? So let's suppose that we want to try and write a monad in which every action that we run must take less than 1 second. Right? So let's call this timed. And all it's going to do is just going to wrap an IO action. And I'm going to stick in an incantation here. If this makes no sense to you, then don't worry too much about it. The interesting part here is that is in the definition of monad here. And like I said, in Haskell, bind is normally primitive, not program composition. And so I need to define what bind does for this new monad. Okay, so we get 2 programs, f and g. Remember, g takes 1 argument, f does not. And I need to explain how to stick these 2 things together. Now, f here is my first action. So what I can do is I can stick in a timeout around the call to f of 1 second. And then look at the result. And then if there is nothing, then I can throw some exception. And if it's just a result, then everything is fine, and I just continue with G. And for timeout, it's just a new kind of exception that I can just define here. Okay. All right. And finally, I need a way to run timed actions, which just means unwrapping it. So let's see an example. And let's go back to the function A and function B that we had at the very beginning of the episode. So function A, remember, was printing this string and then returning x plus 1. Now this is a timed function. And just to make things a bit more interesting and just so that everything takes a bit of time, this thing is going to take 3/4 of a second, right? Which is well below the limit, right, of 1 second. So it should just work. And the other function we had as well, which was function B, what it did was print world and then returned x plus 2. And again, we've given this a 3/4 of a second delay. Okay. So what we can do now is have some example where we call these functions. And let's just, for the sake of argument, say that we are going to call function A twice. So we call function A with the initial argument. Then we call function A again with the result of the first one. We do this one more time, except now we call function B. And then the result is the result of function B here. What did I do wrong?
I don't see it
Is
either.
this-
Must be something weird. Unexpected to lock. What?
Oh, I see. Sorry.
Ah, that is indented. Oh
It was
my.
indented,
Yeah.
right, Apologies. Okay. Good.
Yeah.
Um,
Yeah, our audience just figured it out at the same moment.
Thanks, guys. Okay. So all we did is call A twice and then call B. So we would see hello world, and then some final results. So let's try this. So we could say runtime example 1, and we need to pass in an initial argument, and we see hello world, and every action takes 3/4 of a second. Okay, makes sense. Now, finally, let's suppose that we are just a programmer, right? And we're looking at this code here and think, oh, you know what? This pattern here, where we call function A twice, that is often that we're doing this so often. Let's make that its own function. So we can define a new function called, I just call it fun AA here, and it literally just does fun A twice, right? Which means that I can now define example 2 to be the same thing as example 1, right? I just refactored, right? This is just a refactoring, and if you would see this PR, if this would come in as a PR review in your, on your repo, then you would presumably say this is just fine, right? I've just replaced this thing here with a call to fun A, which does exactly that. Okay, so I'm going to call fun AA with this initial argument, and then I am going to proceed in the same way as I did before with the list. Right, so hopefully everybody would agree that this is a harmless refactoring. I've just taken out a bit of code and stuck it into its own function.
Well, I mean,
well, okay.
Everybody would agree. I hope not. I mean, if they've
been paying
attention, they should not.
Fair enough. So let's try. So if I now try example 2 with some initial argument, it runs, and then suddenly we get an exception, right? And a timeout exception. So what went wrong? Well, the problem is that example 1 is really the same thing as we're first doing fun A twice, right? So we do fun A, then we do fun A again, and then we do fun B. And it's like this, right, with the brackets on the left. Whereas here, we've stuck these two things together. Right, so if I just move this down a little so we can have the two examples better closer together, then this is actually fun B after fun A, fun A. Now, we said at the very start of this episode, when we started talking about laws, that these two things should be the same, right? That's what the law says. Which means that we have written an instance of monad. We have tried to make a monad instance, which does not satisfy the laws and therefore is not a valid monad instance. Does it matter? Yes, it matters, right? It means that basic refactorings no longer work. So the problem here is that this definition of bind doesn't really make sense. We said f must be the first action that we're running, and we try to give it a 1 second timeout. But of course, f itself could also be the composition, but there could be another binds in there, right, of other actions. And if that happens, then this timeout would be applied to the composition of those two things, right? So in example 1, we have a 1 second timeout for A, another 1 second timeout for the second A, and then a third 1 second timeout for function B. Whereas here, we have a 1 second timeout for this composition, which together will take 1.5 seconds, which exceeds the timeout, and then another timeout for function B. So that's why we're getting a timeout here. So this is not a correct Monad instance.
Yeah, so I mean, perhaps just to reiterate, I mean, it's like sort of course, this is accepted by Haskell, and of course, you can always argue, oh, couldn't I just do this? But the point here that Etzko is trying to make, and I think it's very, very valid, is that we are learning to think about sort of what are valid transformations about programs intuitively over time. And like in particular, if you look at this example in do notation, we might make such a refactoring without even thinking about it, right? And this is becoming so deeply ingrained. And I think you can, of course, then argue, is that a good thing? But I think, yeah, it is a good thing that we are learning to identify certain classes of programs and that certain transformations are safe. But in order to maintain the safety of such transformations, that's exactly why we need laws, right?
Exactly. Yeah, well said. Are there any final questions?
No, there's been very little chat, but no real questions.
Okay, good.
Yeah, thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to either ask any more questions right now in the chat. We'll leave it open for a little bit, or afterwards place them in comments. And actually, we just got a question right now, which we might still be able to briefly discuss, by Matthias. I guess this refers to the
probably the timeout,
timed to the timed. Yeah, I know this might be besides the point, but how would you implement it then?
So what I would do is I would define a type for primitive actions, and then a way to compose them, and in the composition say, like, when you compose, like when you take a primitive action, you can impose a timeout on it. So you'd have to make a distinction at the type level between composition and the primitive actions on which you want to impose timeouts. Yeah, that's probably what I would do.
Yeah, I think I agree with that. Okay, yeah, so as I said, I mean, more questions are welcome, either now in the chat or afterwards in the comments for the video, and we'll be back as usual in a couple of weeks. We haven't decided the exact date yet. Goodbye.